Retrieval gets candidates. Reranking decides what the user actually sees first. This is the pattern you'll be able to implement by the end, which pulls rough matches, then re-ranks by scoring each query item pair to put the best first. I'm Professor Pi, teaching AI foundations with simple Python. Search systems usually cut work into two stages. First, you fetch a small set of plausible matches. Then, you spend more compute to pick the best one. Re-ranking with a cross-encoder is a clear way to make that second step smarter. It reads the query and each candidate together and scores the pair. So subtle signals that a simple lookup misses can change the order. At a human level, success means users see the most useful result first. That reduces clicks, improves metrics, and feels fast when you only re-rank a handful of candidates. We will keep the example tiny, so the idea is obvious, not buried in engineering. The core idea is simple. Use a cheap lexical filter to get a short candidate list. Then, apply a joint scorer that inspects both texts together. Think of it as a referee reading both question and answer before deciding. Strengths are better precision. The trade-off is extra per pair compute. We will build a compact pipeline that shows this pattern end to end. It will fetch 3 candidates with a quick overlap score, make pairs with the query, and then rescore them with a small cross-encoder-style function that rewards precise phrasing. That keeps the code short and the logic clear, right before we look at the first snippet. This snippet retrieves a top 3 candidate pool using a simple Jaccard score. We start with a tiny, in-memory list of documents and a query string that asks for reversing a list without copying. The variable Qt holds the query tokens as a set, and the list sims stores a pair of document index and Jaccard similarity between the query and each document. Jaccard compares token overlap to union, giving a quick lexical relevance estimate without embeddings. We then sort sims in descending order and keep only the top 3 matches in the list top. The printed baseline top ID shows which document the lexical stage would surface first and its overlap strength. Now we'll turn those candidates into inputs for the cross-encoder. This example prepares query document pairs from the candidate pool for re-ranking. The list cans extracts the document IDs from the earlier top results, so we can focus on a small, promising subset. We then build pairs as tuples of the original query and each candidate document, which is the natural input shape for a cross-encoder that reads both texts together. To get a feel for the pool, Sizes collects token counts per candidate, and avglen reports the average candidate length. The printed pairs and avglen confirm a compact re-rank set with short texts that keep the next stage efficient. Next, we'll score the pairs with a lightweight cross-encoder-style function. This code rescoring the candidates with a small cross-encoder-style interaction function. The function xscore reads the query and document together. Base reflects token level alignment. Entail adds a strong bonus when the queries without copying intent is supported by the document mentioning reversed, and penal subtracts when the document suggests slicing, which implies copying. This mirrors a cross-encoder's joint attention over both texts, but through lightweight, interpretable rules. We compute scored pairs for the candidate IDs and sort them by the new score. The printed re-rank top ID shows the best match rises to the top and reports its cross-encoder score. Now let's tweak a parameter to see how the re-rank changes. This example explores how a single parameter changes ranking confidence. We lower phrase boost in xscore to reduce how strongly the reversed queue supports the queries without copying intent. The list scores recalculates cross-encoder style scores for the same candidates and ordered sorts them by these adjusted scores. The variable margin measures how far the top candidate is ahead of the runner-up, which reflects how decisive the re-rank is. Increasing phrase boost strengthens the entailment queue and typically widens this margin. Decreasing it softens the queue and narrows the gap. The printed CE margin reveals the current confidence spread after tuning. Finally, we'll combine retrieval and re-rank into a single call. This snippet stitches retrieval and cross-encoder re-ranking into a compact baseline. The function re-rank first builds a Jaccard-based similarity list sims to fetch a small top K candidate pool, keeping the pipeline fast. It then computes cross-encoder-style scores with X-score for those candidates, capturing joint query document signals, and selects the maximum as the winner. You can increase K for more recall at the cost of extra rescoring work. Raising phrase boost prioritizes strong entailment evidence. The final print shows the top document ID and its score, demonstrating a complete re-ranking pass that promotes the most relevant result. If you map this toy setup to a real system, the same pattern holds. Replace the tiny document list with your corpus. Swap Jaccard for a fast vector or lexical index, and replace the toy X-score with a real cross-encoder model. The pipeline still fetches a small pool, and then spends more compute to decide the order. Recap: it is a two-stage pipeline that fetches candidates, then re-ranks by scoring query and document together. Use it when you need higher precision than a single-stage retriever can give. Caveat: re-ranking is more compute per candidate, so keep the candidate pool small. For one concrete next step, tune the phrase boost or the candidate pool size K and measure how accuracy and latency trade off. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.